Our last speaker of the day is Andy Ingersoll, who's a professor of planetary sciences at Caltech. Andy is one of the few people who's an expert both on the Earth's atmosphere and on planetary atmospheres. And he holds the distinction of having published a research article on the atmospheres of all the planets in the solar system. And maybe unique. There we go. So, and he's also the editor of the scientific journal Icarus. So, Andy Ingersoll.
I'm going to take you on a whirlwind tour of the solar system. And if you think you've seen climate extremes so far, you'll really see them during the whirlwind tour. The whirlwind tour follows the course of my book, from Venus all the way out to the outer solar system. But my book is also, because actually just a fact of life in my field of planetary science, planetary climatologists, and there are people like that, learn their climatology from reading textbooks on the Earth. And that's fine. We know a lot more about the Earth than we do about the planets. But I decided, let's put in a little bit of the basic physics into a book that is basically a whirlwind tour of the planets. So if you ever get to read my book, you'll see the tour, but then there'll be boxes sort of fenced off from the narrative where the basic climate physics is presented. So it's both a textbook and a tour. What are the lessons? Why do we study the climates of planets? Well, I don't know why we study them, but let me tell you some of the lessons. One is humility. All of our accumulated knowledge about the Earth in general, but in this case, the Earth's climate, doesn't prepare you, and this has happened time after time, it doesn't prepare you for what you're going to find when you go to a new world. Your imagination is just too limited if all you've done is study the Earth, no matter how smart you are. Another is that there really are examples out there of two states to a system, like the present Earth and the snowball Earth, or the present Earth and Venus. There are, and therefore there are possibilities of truly dramatic, maybe catastrophic climate change that may not happen in our era, but maybe in a billion years they could happen. But there are plenty of examples out there. Talk about weather for a moment. Predictability. You know that a weather forecast is pretty worthless out beyond a week. You don't plan your vacation based on what you read in the paper for 6 days from now. Or maybe you do, but you cross your fingers. We can predict the weather years in advance on some of the giant planets. The Great Red Spot is a big hurricane or big vortex on Jupiter. It's been around for 300 years. You can extrapolate its lifetime pretty far ahead. So the limited predictability we have for Earth is not really a fundamental theoretical property. It's just the way Earth works, and we should try and understand the differences. And the last surprise is that the Earth is the wimpiest planet in terms of wind speeds. And in fact, wind speed gets faster and faster as you move out in the solar system, quite unlike what you would expect given the lack of sunlight out there. Okay. So that's the one. I could sit down now, but I've got a lot of nice pictures, so let's do that. This is the disk of Venus, and you're seeing the sulfuric acid clouds. And Venus used to be, before the space age, it used to be called the Earth's sister planet. because it's similar in size. It's the closest in orbit to the planet. What else is resemblance? Then radio telescopes, which can peer through the clouds and measure the surface temperature, said, no, guys or girls, it's hot enough to melt lead on the surface of Venus. So the Earth's sister planet is actually a hellish place. But that's a puzzle, because we've also, during the space era, we've learned that there are other similarities between Earth and Venus. The global complement, the global abundance of carbon dioxide is rather similar, and that means within a factor of 2. We're planetary scientists here. Factor 2 is nothing in my business. But the carbonate rocks on Earth and the total huge, massive atmosphere of Venus, which is carbon dioxide, are kind of comparable. And the amount, there's a little bit of nitrogen in this 90 Earth atmosphere here, 90 times the Earth's atmosphere, and it's mostly carbon dioxide. But there's a little nitrogen in it. And so the nitrogen on Earth and the nitrogen on Venus are rather similar. And the argon in Earth's atmosphere and the argon in Venus's atmosphere are rather similar. So they really look like they're sister planets, except with one huge difference. We have oceans, and Venus has a little bit of water vapor in its atmosphere, and no liquid water, and certainly no solid water. So the possibility exists that they were born alike, and Venus went one way in its evolution, and Earth went the other. And there's even evidence that Venus has lost a whole ocean over geologic time, and it has to do with the isotopes of hydrogen, or, if you like, that little bit of water in the Venus atmosphere. And here's the isotopic evidence. This is the deuterium to hydrogen ratio for a lot of bodies. It's hard to measure it if you don't live there, but you can do it spectroscopically. You can look at methane with a deuterium replacing the hydrogen, and that's what's done for all these objects. And it's kind of down in this 10 to the minus 4 times 2 range. But then there's Mars, and Venus is off scale, 150 times deuterium to hydrogen, which is a sign that some process has changed the deuterium-hydrogen ratio on Venus. The kind of process, the one we know about, is that hydrogen escapes from the top of the atmosphere, drifts away into space. Deuterium, being a little heavier, twice as heavy, escapes more slowly, and so the deuterium that's left, the D-H ratio that's left builds up. And this 150 factor indicates that a lot of water has been lost over geologic time from Venus. We don't know how much, because the differential rate is not, it depends on temperature and a lot of other things that we don't know. But it is a powerful evidence that Venus may have lost an ocean. It could have lost an ocean of water. We don't know for sure, but it's evidence that Venus has lost a lot of water. Why might it lose? Why might Venus have lost its ocean of water? Well, you heard about water vapor feedback, where if you warm a place up enough, then you'll get more water vapor. Water vapor is a greenhouse gas. That warms the place up further. That produces more water vapor, and so it goes. And that runaway feedback occurs if you're pumping enough heat into the system. If you take the Earth and move it to the orbit of Venus, it's possible that this runaway greenhouse could boil away the oceans, subject the water to photodissociation, and lose all the hydrogen. And so it's scary possibility that the runaway greenhouse, this water vapor feedback, could get out of control if you put too much heat into the system. Don't worry about it for the Earth for the next billion years, but that's the spirit of what we do in planetary science. Okay, a couple other things about Venus, and then we'll move on. This is the budget of energy at the top of the atmosphere. This is latitude. This is a profile of the absorbed sunlight. Crudely, Earth satellites do a much better job than this, but the planetary equivalent didn't have such good resolution. But this is the absorbed sunlight. Obviously, you absorb less per unit area at the poles than you do at the equator. And the green is the outgoing long-wave radiation, the thermal emission. And it's less at the pole than it is at the equator because it's colder at the pole than it is at the equator. Here's the same for Venus. Venus is a very bright planet, so it actually absorbs less sunlight than the Earth does, even though it's closer to the sun. That's today. It's covered with the sulfuric acid clouds. The interesting thing I want to point out is that the emitted long-wave radiation, which is basically proportional to some power of temperature, is pretty flat for Venus, and it's decidedly unflat for Earth. That's telling you that Venus is doing a better job at spreading the heat around than Earth is. It's a fundamental property of atmospheres. How good are they at evening out the temperatures? Well, Venus is better than Earth at that. Why? Number one, it's got an atmosphere almost 100 times more massive than Earth's atmosphere. Number two, it's a slowly rotating planet, and rotation kind of inhibits motion between equator and pole. And I'll just leave it at that. No, there's a question. Why doesn't the ocean, which is even more massive than Venus's atmosphere, why doesn't the ocean step in and transport a huge amount of heat toward the pole? Why is the ocean, as wimpy as it is, in the, that's your question for you, why is it only 1/3 of the atmosphere? My feeling is that it's heated at the top, and whereas Venus's atmosphere, the sunlight does get through it, but who knows? Okay, I alluded to this one. Now, Venus spins backwards, and so this is its wind speed as a function of altitude here. Mount Everest would be about 9 kilometers high, so we're way up high here. But the winds up at this is the cloud tops up here. The winds up here are twice as fast as the Earth's jet streams. And as you'll see on the giant planets, they're even stronger. And at Neptune, the farthest from the sun, is the fastest of all, which is totally puzzling. But let's move on, because we have to move on. Okay, now here's the same side of Mars with and without a global dust storm. And all I'm doing is just giving you puzzles. I'm not going to answer any of them. These global dust storms are like El Niños in the following sense. They occur at a particular season. It turns out it's the season when Mars has an eccentric orbit, and so when Mars is closest to the sun, you sometimes get a global dust storm. But like El Niños, you don't get them every year. A few years go by, there's no global dust storm, then you get a big global dust storm at that particular season, and then a few years go by. So that's like El Niño. El Niño comes at Christmas time, but not every year. And we say, oh, we understand that. It's the inertia of the ocean. When the ocean is doing its own thing with long period There's no ocean here, so it's a puzzle. I think that, I think it has something to do with the time that it takes the dust to settle out of the atmosphere and for it to build up on the ground until it's ripe for another dust storm. But somewhere we've got to find the long time constant of the system, and it's not the ocean. A little more about, these are dust devil tracks. So the dust devils, which are very numerous on Mars, they strip off the dust and leave these tracks. I'm not going to say much about them. All right. Here's a picture. The sun is coming in from the right side. So this is the inside of a crater. This is the shadow of its crater. And you'll see this channel that looks very much like a dry riverbed. Probably is a dry riverbed. It's an old dry riverbed because it's been sitting out there to accumulate craters. And here's a sort of valley network of streams that maybe came together. All this happened several billion years ago, and that resonates with a problem that geologists, Earth geologists have had for decades, which is the evidence that the climate was warmer several billions of years ago than it is today. And it's called and then the climatologists, Earth climatologists first, but now Mars climatologists, they go down the hall and ask the astrophysicists, well, what was the sun doing? And the astronomers say, well, the sun was only 70% of its current luminosity back then. And so why was it warmer and wetter when the sun was fainter? Well, no one knows, but they can give it a name. It's called the faint young sun paradox, and Mars is a good example of it, just as Earth is. Whoa, it's wonderful just to leave these problems lying there. This is what Mars does today. So this is the two Viking landers, Viking Lander 2. This is the pressure, and this is time. And these periodic cycles, which repeat so beautifully, are years. And so you're measuring the pressure at these two lander sites. Viking Lander 2 was at a lower elevation, so the pressure was higher. That's the blue. Viking Lander 1 was at a higher elevation. But they go up and down together very beautifully. What's going on? This is the growth and retreat of the polar caps. So when you have CO2 atmosphere, as we do on Mars, and it's only fairly low pressure, 9 millibars, where 1 bar is the Earth's sea level pressure, the annual accumulation, twice a year actually, one at each pole, the annual accumulation of carbon dioxide, which is main component of the atmosphere and also of the polar caps, it sucked down the pressure of the whole atmosphere, sort of breathes in and out every seasonal cycle. Okay, and last, the water. This is the history of water during a year. Here's 90. This is an angle that represents the position of Mars in its orbit. Water comes pouring out of the North Polar Cap in its summer season really. But when I say pouring out, this is water vapor, and it's equivalent to a lake 10 to the minus 4 meters thick. So the total water in the Mars atmosphere is, well, it's actually less than that, 75 microns thick. And then it all condenses out. So so Mars is very cold, and there's not much water vapor in the atmosphere. And it would take 1 million years to move this polar cap to the south. And so Mars is almost inert on Mars, and I think I'd better move on from there. Go on to another one. This is Titan. Titan is a moon of Saturn. It's got an atmosphere more massive by almost a factor of 10 in the mass above your head. More massive than Earth. It's mostly nitrogen. Interesting thing about Titan is that it's got a hydrologic cycle. It's got rivers, lakes, clouds, rain. But it's not water that is doing all that. It's methane, which we think of as natural gas. But it's so cold out there that a familiar gas molecule becomes a liquid molecule out in the outer solar system. And we have a, here I'll test your intuition. You have 1% as much sunlight available to drive your weather out at Titan. That's Exhibit A. You have a wet atmosphere in the sense that it holds a lot of methane. Actually, the latent heat stored in the Titan atmosphere, the heat needed to evaporate the methane is greater than the latent heat stored in our atmosphere as water vapor. So you have a lot of stored energy, latent heat energy, in the atmosphere, but you have very little power coming in. The atmosphere could go two ways. It could have very light drizzle continuously, or it could have nothing at all for long periods of time and then downpours or something in between. It's kind of the 0 times infinity problem. Well, Titan has chosen the second. These are some of the lakes taken by a radar, which peers through the clouds, and you see river channels. Here you have channels that were carved by flowing rivers, and a light drizzle continuously precipitating out of the atmosphere is not going to carve these. These are rather big channels, hundreds of meters across. You need a downpour to carve a channel like that. And so somehow, Titan has chosen the very infrequent, very violent weather option rather than the steady drizzle option. Go figure. Okay? My friend, the giant planets. The Great Red Spot was there shortly. It was as soon as someone had the technology to see it, they saw it. Galileo didn't see it, but the telescope was improving in the decades after he invented it, and Robert Hooke saw it. And it's been there ever since. There's no solid surface to give this fluid structure its longevity. It's just a fluid structure. It's not stationary. Everything on Jupiter rotates with approximately a 10-hour period, and relative to that average rate, the red spot mostly chugs to the west, but sometimes it reverses itself and chugs slowly to the east. I was a member of the Voyager imaging team, and Voyager was slowly approaching Jupiter, and this happened with every one of the giant planets. And we would take pictures of the features from great distance. We said, okay, in the last final days, Voyager's going to go zooming by, and we're going to take close-up views of this great. When we're very close, the disk is much too big for us to photograph all of it. So we're going to have to make choices about which things, during those final days, which things we want to view up close. And so we asked the engineers, well, how late can we get the camera pointing commands to you and they said 3 or 4 weeks. So we had to make a weather forecast 3 or 4 weeks in advance to command the camera, tell it where to look during the last couple of days. And we finally used junior high school mathematics. You plot it on a graph paper, you lay a ruler on it, and you said, spot A will be over here and spot B will be up there, and we hit all the targets. And that's with junior high school mathematics, not a GCM. Actually, more about Jupiter. Every one of these bands has associated with its edges a jet stream, either eastward relative to the average or westward relative to the average. And there's 6 eastward jet streams in each hemisphere, as opposed to 1 basic mid-latitude jet stream in each hemisphere on Earth. That's an interesting question. Actually, Gareth Williams here at Princeton made some of the fundamental advances in understanding that. And the winds are 3 times faster than the jet streams on Earth. And Jupiter is the wimp of the giant planets. As you go farther out, all these atmospheres with no bottoms, no surfaces underneath, the winds get stronger. The weather is incredibly stable. Every jet stream that was observed in 1979 was also observed in 2000. I'm not showing you the winds. You could ask, sometimes people ask, is the red spot a hurricane? Well, it's an anticyclone, but that's maybe okay because we're looking at the top of it, and the tops of hurricanes are anticyclones. It's quiet in the middle. This is the winds vectors that we measure. It's quiet in the middle. It does not seem to get stronger, so it's unlike a hurricane in that respect. And then fundamentally, there's no ocean underneath. So that kind of changes the game. It's not a very good hurricane in that sense. But it is very stable. I'm going to just zip along here. Interestingly, the temperatures, let's look at this scale. This is temperature at the level where the infrared is leaving the planet. It's flat. It's flat. These bumps and wiggles are not very big. They're associated with the jet streams. But all of these planets are pretty nearly have the same temperature at the equator as they do at the poles, quite unlike the Earth. And the explanation may be similar to the explanation for Venus. Okay, wind speeds. Here's Neptune. It looks sort of like the Earth. The winds are to the west at the equator, to the east at the poles, but the difference in speeds is 600 meters per second, which is very big by terrestrial standards. Okay, I think I'll finish with Saturn. This is the way Saturn looked in, I think, January of 2011. 20 years had passed, and Saturn looked basically like this since 1990. Up to here, Saturn looked totally bland and totally boring. And then it erupted into this thing. The radio receiver was catching the static from lightning bolts, counting the lightning flashes as fast as it could, and that was 10 of them per second. We could see the lightning flashes on the day side of Saturn. And this thing lasted for 6 months, and it's pretty much gone. And these violent storms occur every 20 or 30 years. There have been 6 of them. The first one that was observed was 1876. There may have been more before that, but no one was looking. And this this is quite different from Jupiter. It's quite different from Earth. It's got something to do with moist convection because there's so much lightning in it. And we don't understand it. And it's telling us something that the view we have of convection, which is sort of a steady process that keeps pumping moisture into the atmosphere, it may not apply on other planets, and other planets may be much more intermittent in the way they work. Stop there.